Okay, welcome back, everyone. Thanks for coming again. Let me tell you a little bit about what we'll do today and what we'll do the next time. Today I want to talk about combinatorics at low temperatures, and maybe this is like of all the lectures, this is the point I most want to get across in these lectures, is just some idea of how do we use certain statistical physics techniques to analyze a very typical problem in combinatorics, which is how do you understand near extremal examples? And I think hopefully people that listen to these lectures, maybe you'll find some applications of these tools or ideas. So good. So today what we'll do is we'll first just summarize the discussion of the cluster expansion, the convergence criteria from the last lecture, from lecture 3, just to recall what is a cluster expansion and how do we know when it converges and what do we derive from convergence, and then I'll move on to this idea of low temperatures, and I'll give first some just high-level intuition for how you want to view low temperature models with some pictures. Then I'll introduce maybe the important thing today is the idea of an abstract polymer model. I'll give some examples. I'll translate the convergence criteria that we had for the cluster expansion to this setup. And then I'll sort of work through one example about how to analyze things at low temperatures. And I'll talk about a fairly simple example, the Potts model on expander graphs, because it's rather simple. And then for the next lecture, I'll probably take half the time to continue this topic, and then with the second half of the next lecture, I'll sort of give you some open problems related to sphere packings and things like that. But yeah, this topic will go over to the second half of the first half of the next lecture. Good. So let's just summarize what we talked about last time. We talked about the cluster expansion. And the setting for the cluster expansion was the multivariate hardcore model on a graph. So we have this hardcore model of independent sets, but now we're thinking that each vertex V comes with its own fugacity or activity, lambda V, and they don't have to be the same. The cluster expansion, we said, was the multivariate Taylor series for the log partition function in the variables lambda V. Okay, and we showed what the form was. The form was the sum over some connected object called a cluster, which is a tuple of vertices from the graph. We had some combinatorial factor, the Ursel function, that just depends on the graph, the incompatibility graph of this cluster, and then we have the product of weights. So that's the cluster expansion. It's a formal power series. And so, of course, we want to know when does it converge and when can we actually use it to, for example, compute the asymptotics of the partition function. When can we use it to deduce some probabilistic information about correlation decay and so on. And so the key criteria we discussed was the Kotetsky price convergence criteria. And it has this nice compact form. So what you want to check is that for every vertex in your graph, for all V, if you sum over all the neighbors of V and V itself, absolute value of the activity function, e to the a of u plus b of u, and here a and b are some functions from v to, say, 0 infinity. We want this to be at most a of v. Okay, and so this is some condition on the weights being small. Want the way, or I should say the fugacities, want activities to be small. Okay, and so the idea is if the typical independent set in your graph is very small, then somehow we're able to control the dependencies between vertices, and in a very nice way in this series form. Very good. Oh, Wojtek asked a great question. What is the role of b? You can certainly take b to be 0. So that's this function here. you can take B to be 0, and what you'll conclude is that the cluster expansion converges and Z is not 0. Actually, let me just show you, I'll pull up the slides. Let me show you the conclusions of the Kotetsky price condition. This is a great question. Right, okay, so let's look at the conclusions. This conclusion certainly holds. This conclusion certainly holds. What you gain from having a positive function B are the 3 and 4, conclusions 3 and 4. And so 3 and 4 basically say, give you explicit tail bounds and exponential decay. And so here we're summing over clusters where the sum of the B's is at least T in both cases, and we get e to the minus T here. And so if you can take B to be positive, then you get some explicit exponential decay of the tail of the series. And so this really tells you I can truncate the series right here. Okay, so you're right. If you just care about convergence, it's not necessary, but it really gives you some power to be more explicit. Great question. Thank you. Good. And so that's the idea. We'll sort of see some more intuition for how to choose these functions A and B when we get to the next chapter. I'll just sketch quickly the example that's in the notes. I think it's worth sort of working through this example on your own, just to, for once, at least one time, do the actual explicit calculations of the first few terms of the cluster expansion. So the setting is that G is a delta regular graph with no triangles on n vertices, and lambda is quite small. So it's smaller than n to the minus 1/4. Okay, and then the result that you can get by applying the cluster expansion is the asymptotics of the partition function. And so what are the asymptotics? Well, it's this 1 plus lambda to the n. What do we view this as? This would be the partition function if G had no edges. Okay, so if you just were a graph with n isolated vertices, the partition function would be 1 plus lambda to the n. And so what the first couple terms of the cluster expansion will measure will be what is the deviation from this empty graph. Okay, and as I said, you'll recognize this term. This is like what you get from Janssen's inequality. And as I mentioned, Wojtek's paper on the probability of non-existence, it will give you the same series. So this is not anything you need the cluster expansion for, but it's a good illustration. And so where do these terms come from? What are the clusters in this case? So now, you know, we have this univariate hardcore model. So every vertex has the same activity. And clusters, again, are tuples of vertices. And so there's one type of cluster of size 1. It's a single vertex. Its Ursel function is 1. There's n of them. Okay, I should say how many. There's n, and you get a lambda. And so here, when we look at the cluster expansion, the clusters of size 1 consisting of single vertices give you this n lambda here. Okay, there's 2 different types of clusters of size 2. You could have 2 copies of the same vertex, and so there's n of these. Or you could have an edge, and remember these are ordered, and so there's n delta of these. And then the Ursel function in this case, in both cases, the graph that we're considering is an edge, because in this graph h of gamma, if you have the same vertex, we're putting an edge. And so what terms do you get? You get the n lambda squared over 2 from this type of cluster, and you get the n delta over 2 lambda squared from this type of cluster. Okay, and then we can go on. There's 3 different types of clusters of size 3. There's 3 copies of a single vertex. There's an edge with one of the vertices doubled. And then there's a V in the graph. Okay, and because our graph is triangle free, we have formulas for the count of all of these just in terms of n and delta. And I mean, almost surely I made a mistake in calculating this, so I'm not sure this is right. It's a good exercise to check to find where I made my counting error, if I did. But this is how you get the next term. And if you check the Kotetsky price condition, what it will say in this case, when lambda is little o of n to the -1/4, it will say that all the rest, the tail of the series, if you choose B appropriately, will tell you that the rest of the series is the whole thing in absolute values little o of 1. And so this series gives you the asymptotics of z when you exponentiate. The first three terms somehow give you the asymptotics of 1 plus lambda to the n. This is just the first three terms of the Taylor expansion of log 1 plus lambda, and these two terms give you the correction. Okay, and that's the correction that appears here. Okay, so any questions about that? That's the cluster expansion, the convergence criteria, and a little example of, how do you go about computing things? You start to write down what the clusters are, calculate this combinatorial factor, and count things. Okay, very good. So what we'll do next is move on to low temperatures. And so low temperature, I want you to think this is like strong interactions. And I'll use the word low temperature to mean like high fugacity. So if you're talking about hardcore model, high fugacity or high density. I'll call that low temperature, even though there's no temperature, but I really mean strong interactions. Okay, so we're trying to understand some statistical physics spin model when the interactions are strong. In particular, what do we expect to see? We expect to see long-range correlations. The cluster expansion will not converge. And so on. And we might have phase coexistence, meaning that typical configurations align with more than one possible ground state. Okay, so let me show you a picture, and maybe this picture will tell you the most important thing you'll get from this lecture. So it's actually three pictures. So here's three pictures, and again we're looking at the hardcore model on Z2 with periodic boundary conditions, so some torus. And I've done three simulations. The first at very small lambda is 0.05, and the second two at lambda is 4.1, so large lambda. And of course, so what do we see? So in the first picture, we see a very sparse independent set. And so these the occupied vertices are kind of far apart. They look fairly disordered. There's not really any pattern of where the even or odd. So evens, let's say, are in red and odds are in blue. There's no real pattern. There's disorder. You can imagine, and it's true, that correlations decay exponentially fast here. Of course, this is just one realization. And then when we look at large lambda, what do we see? Well, I did two different samples from the model. And in one case, we ended up with an even dominated independent set. So I forgot what I said. Let's say red is even. So this third picture, almost all the occupied vertices are even. There's some gaps, some missing vertices. There's also a few little islands of odds. And then on the other hand, we get this odd dominated independent set where there's the picture is basically reversed. And if we're talking here about the discrete torus with even side length, there's symmetry. And so basically what you expect is 50% of the time you see something blue dominated, and 50% of the time you see something red dominated. And so clearly there is very strong long-range correlations. If I tell you that this vertex over here, right, is red, is occupied, and it's even, then this really tells you you're more likely to be in this picture, and so it's much more likely that a vertex over here is red or even occupied. Okay, so the long-range correlations are very strong. But now what I want you to do is sort of like really squint your eyes and think, do these three pictures really look that different? Okay, so obviously they look different, but imagine that I just I'm doing like Microsoft Paint or something, and instead of having a white background, I choose a background that's like a red and white checkerboard. Okay, then these little blue islands, their pattern doesn't look so dissimilar to the pattern of red and blue occupied vertices in the low density regime. And similarly, if I just thought of my background as being a blue and white checkerboard, these little, I'll call them defects, these defects, they look very sparse, far apart, kind of disordered. It's not clear that if I tell you there's a defect here, that you should believe anything far away about where another defect should be. And so this is the big idea here, that if we want to understand the low temperature or the strong interaction, high density regime, what we should think about is not think about our original spin model, but we should try to think of a new spin model or a new statistical physics model where the objects we care about are these defects. Okay, we care about now we want to create a model capturing the defects and not the original spins. And what we can hope is that somehow by taking this perspective, we've switched from a strong interaction, low temperature regime to a very weak interaction, high temperature regime, where we have all the tools that we have introduced. Maybe the cluster expansion works if we're just talking about defects. And so that's the idea of what we'll do today. And this is, of course, a very important technique dating back, at least 50 years in statistical physics. But we'll see that it actually really works well in combinatorial problems as well. So any questions about that picture and the idea of this? We really want to change perspective. We want to go from the strong interaction regime to the weak interaction regime by thinking of defects instead of spins. Okay, so how will we do this? Oh, great. Is there a name for this method? Yes. Yeah, so it has a couple names. So on ZD, okay, and so this is where statistical physicists usually carry through this program. This is called Pirogov-Sinai theory. Okay, and the idea is, it's actually, Pirogov-Sinai theory is a bit more sophisticated and more advanced than what we'll do today. The idea here is, it's not that you're not looking at necessarily defects from the ground state, you're looking at contours separating, let's say, different regions of ZD dominated by different ground states. And so I can do a little sketch here of what I mean. So imagine that you're thinking that you're in a red dominated, in the Potts model, let's say, red dominated configuration. You might see some deviation from this, a contour, where inside the contour you're looking blue. But inside your blue island, you might have another red island, okay? Or you might have a green island. Okay, and the idea of Pirogov-Sinai theory is that the objects that you're going to study are these contours, not the entire defect, but the sort of boundaries separating them. So that's one fancy name for this theory, Pirogov-Sinai theory. What we'll use is just one component of this, which is the next thing I'll introduce, which I'll call, which is called abstract polymer models, or polymer models. Okay, and so polymer models are used to carry through Pirogov-Sinai theory, but just on their own, there are some simpler version of this idea of turning defects into their own spin model. Okay, and I think I have it in the notes, but a great source for learning about the way they use all of this stuff in statistical physics is this textbook by Friedli and Villanek, Statistical Mechanics of Lattice Systems. It's a really fantastic textbook. It has a chapter on cluster expansion, has a chapter on pure Gaussian theory. It really, I can't recommend it highly enough. Good. So, so how are we going to carry this out in combinatorial settings? We're going to use this abstract polymer models. And so let's think of at a high level, what is the multivariate hardcore model? There's two properties. So the multivariate hardcore model, which was the setting for the cluster expansion, it has two properties. One is that configurations are collections of objects satisfying some geometric exclusion property. Okay, so in the case of the hardcore model, of course, this means these are independent sets. You're not allowed to be neighbors, but this is just some geometric exclusion property. And importantly, the weight in the probability in the partition function, or the probability mass, the weight of a configuration factorizes over the objects in the collection. So in the case of this hardcore model, it was the product over the vertices in the independent set of lambda v. Okay. But this was key, that the weight of a configuration factorized. And so what we want to do is we want to abstract these two properties. And that's the idea of abstract polymer models. And these were introduced in the very abstract sense by Kotetsky and Price in the same very short paper where they gave their convergence criteria. Somehow they realized that all the ways in which these models had been studied before, you could actually abstract them completely into some very, very general setting. And so here's the idea. So these are abstract polymer models. We have, and it's a triple, a polymer model is a triple. And we'll have some script C, which will be a set of polymers. We'll have some compatibility relation, which I'll denote by this. And we'll have a vector of weight functions, which I'll denote by W. And so C is a collection of polymers. We'll think of this, it doesn't have to be finite, but we'll think of this as a finite collection of polymers. These are our objects. Each polymer, I'll call polymers gamma. Each polymer gamma has a weight function, which I'll denote W sub gamma. Okay, it could be a complex number. I think for all the applications we'll care about, this will be a non-negative number, but has a weight function W of gamma, and there's a compatibility relation. And let's say it's a symmetric compatibility relation. We say gamma is compatible with gamma prime, and we write it this way. And we insist that gamma is incompatible with itself for all gamma. Okay, so the incompatibility relation is symmetric and reflexive. Okay, and this is the abstract polymer model. This collection of objects, the compatibility relation, and the weight functions. And then just from this, we can define a partition function. So the polymer model partition function is, this is xi, this Greek letter. Maybe I should have chosen a letter I knew how to write and pronounce. Let's say it depends on the whole triple, but let's just indicate the dependence on the set of polymers. And what is it going to be? It's going to be the sum over subsets of polymers that are pairwise compatible. And then product over gamma and x, weight gamma. Okay, so this is the polymer model partition function. And then if the weights are non-negative, we can also define a Gibbs measure. Where the probability that you see a certain collection of compatible polymers is the product of weights over the partition function. Okay, so this is the abstract polymer model. Just from this collection of objects, compatibility relation, and wave functions, we can define this partition function. Let's see a couple examples. The first example is the obvious one, the multivariate hardcore model. I mean, in a sense, the abstract polymer model is just a multivariate hardcore model. And here, you know, the collection of polymers is just a set of vertices of our graph. We say U and V are compatible if the distance in the graph is greater than 1. And then the weight function is just the activity function. And so, of course, here, what does it mean, a set of pairwise compatible polymers? This is exactly an independent set. It's a set of vertices which are at pairwise distance greater than 1. Okay, so in a sense that we've just come up with some new names, but we're just talking about a multivariate hardcore model. Somehow this new terminology will be useful in this new perspective. So that's example 1. Example 2, this will start to get more interesting. So let's look at the Q-color ferromagnetic Potts model on a graph G. So recall the Potts model, the configurations are colorings of the vertices by Q colors, and I can even write it, the partition function of this model depends on Q and beta. It's the sum over all colorings of the vertices, e to the beta times the number of, let's call it m of g sigma. M of g sigma is the number of monochromatic edges.
Well, can you remind this ferromagnetic? It's about positive correlation. So
yeah. I'll say exactly what I mean. So the partition function of this model is the sum over all colorings of the vertices, and the weight you give a particular coloring is exponential of beta times the number of monochromatic edges you get with this coloring in the graph. Beta greater than 0 is ferromagnetic. And what does that mean? That means we prefer monochromatic edges. We prefer edges to have the same color at the endpoints. If beta was less than 0, then we would be penalizing monochromatic edges, and that would be anti-ferromagnetic. I mean, so what's the nice thing about the ferromagnetic model? There's Q ground states. And these are the completely monochromatic configurations. Color red, all the vertices red, you'll of course maximize the probability in this model. And from the pictures that we saw on, I guess, the first lecture, depending on the graph, but let's say we're on ZD or something and beta is very large, so we're at low temperature, what do we expect to see? We expect to see a configuration that's dominated by one of the Q colors with some sprinkling of other colors as defects. And so really this is a prime example to try to look at this perspective. Okay, so but now we want to write, now our goal is to write or to interpret this model. Interpret the model in terms of defects defects from the ground states. Okay, so let's imagine here that this is just for imagining purposes, but let's imagine that one of the colors is red, and I'm thinking about a configuration that's mostly red. Okay, and then what do I have? Otherwise, I have, maybe I have a vertex that's blue here and there. Maybe I have a component that's 2 blue vertices. Maybe I have something that's like a green vertex attached to a blue vertex. Okay, but that's the picture I want you to have in mind, is that it's a mostly red configuration, and then there's some small sprinkling of defects of other colors. And so how do I want to interpret this as a polymer model? I'm going to, my polymers will be connected induced subgraphs colored with non-red colors. Okay, so here in this picture, this would be a polymer, this would be a polymer, this component would be a polymer, this would be a polymer, this would be a polymer. Okay, and so I'm given this graph G, and I'm saying polymers now are connected induced subgraphs, but they're not just connected induced subgraphs, they're also colored with Q-1 colors. So they're, you can think of these as labeled connected subgraphs. Okay, good. Now, I want to understand, okay, and what's the compatibility relation? Well, I want the ones that are disjoint to be compatible, and I don't want to say that these two vertices are different polymers. So we'll say that gamma is compatible with gamma prime if gamma union gamma prime is disconnected. Or in other words, gamma is incompatible with gamma prime if their union is connected. And why do we want to say that these are incompatible? We want to say these are incompatible because really we want their union to be a different polymer, a polymer itself. Okay, so in this picture, what I've drawn, I have 1, 2, 3, 4, 5 polymers in this picture. And now what do I want to do? I want to express the weight of a configuration sigma as a product over polymers. Remember, this was a key aspect of the multivariate hardcore model, that the weight of a configuration factorizes over the objects. And so we really want that to happen here. And so let's think about this configuration. We started with this all red configuration. And what's the weight of the all red configuration? The weight of the all red configuration is e to the beta times the number of edges of G. Okay. And so really what I want to understand, and this is a ground state, so this is a maximum weight configuration. What I want to understand is how much smaller the weight of this configuration is with the defects. And so I'm going to say the weight of sigma, right, which is just the e to the beta times number of monochromatic edges. This is going to be e to the beta times the number of edges of G, so the ground state weight, times some product over the polymers, these defects. Let's call our configuration X. And so what is it going to be? So notice that any of these polymers, right, this blue vertex here, all of its outgoing edges are bichromatic. All of the outgoing edges have to go to red vertices. If they go to a vertex that's not red, then the polymer would have been bigger. Right? If one of these edges went to a green vertex, then that green vertex would be part of this polymer. So we know all the outgoing edges of this connected induced subgraph go from a vertex that's not red to a vertex that's red. And so we get a penalty. So we get e to the minus beta, and I'll call this like the size of the edge boundary of gamma. Okay, so this accounts for all these edges that go out of the polymer and hit red vertices. Of course, we also have to worry about edges like this edge, which is a bichromatic edge inside the graph, inside the polymer itself. And so I'll say e to the minus beta times e b, subscript b for bichromatic of gamma. Okay. So this is the number of outgoing edges, and this is the number of bichromatic edges in the polymer. Okay, and hopefully you'll agree with me that we've accounted for all the bichromatic edges in this configuration. Okay. And the great thing is it factorizes. So okay, up to this scaling factor, which we can remove, the weights factorize. And so we can actually write that the Potts model partition function equals, well, we have this prefactor times the sum over all sets of compatible polymers. And then let's call this weight, let's say product gamma and x, weight gamma, where weight gamma now is this, I'll try something very fancy, is this function here. Okay, so what did we do? We rewrote the Potts model partition function in terms with the scaling factor, but then in terms of this polymer model partition function. And this, of course, is e to the beta number of edges of G times this polymer model partition function. Okay, so this is somehow like a key idea for everything that follows. We defined polymers in such a way, and the compatibility relation in such a way that that we really have factorization of the weights over polymers. Now, there's one problem with what we just did, that somehow we wanted to capture the deviations from the all red ground state. But, what you'll see is that we actually accounted for all the configurations of the model, including configurations where it's blue dominated. If you have a blue dominated configuration, you would just have one massive polymer, right? So if this was your configuration and maybe there's a couple red vertices, okay, the polymer in this polymer model would be enormous. It would be like this. And that somehow is not, doesn't really fit with this intuition that we had, that we want to think about the defects as being sparse and far apart and not influencing each other. And so, really we should do something else. And what we'll see is that we really want to restrict ourselves to small, whatever that means, small polymers. Okay, and this will let us actually capture the fact that we're thinking about red dominated configurations, and we really are capturing these small defects. Okay, so any questions on that? That's a good example to keep in mind. Okay, so the next thing that we'll do is we'll just see that this cluster expansion that we defined before, it fits perfectly with this setup. And so, the way to think of this is that the abstract polymer model is literally just a multivariate hardcore model. And so the cluster expansion is nice again. It's the series, so log polymer model partition function equals a sum over clusters cell function of this incompatibility graph, product over gamma in the cluster, weight gamma. And here clusters now are, these are tuples of polymers from the set of polymers whose incompatibility graph is connected. And here, this incompatibility graph, this is according to whatever compatibility relation defines our polymer model. So really, it's exactly the same thing. And then we have the Kotetsky price condition. And what does it say? It says that the cluster expansion will converge if for all polymers gamma, if we sum over all polymers gamma prime that are incompatible with gamma. This, of course, includes gamma itself because we insisted that gamma is incompatible with itself. We look at the absolute value of the weight, and then we have e to the a of gamma prime plus b of gamma prime. And this should be less than a of gamma.
Will, sorry, so all of this is just because this new model, this abstract polymer model, is a multivariate, what is the name? Hardcore model, yes. Hardcore model.
Yes, yeah, exactly. All I'm saying is that because we can interpret this abstract polymer model as a multivariate hardcore model with weights as activities, and the graph, the underlying graph, is this incompatibility graph, then everything we did with this multivariate hardcore model and cluster expansion just translates immediately. Okay, I'm just rewriting. I haven't written anything new. I've just replaced lambdas by w's and v's by gammas. Yeah.
Great.
You know, the one thing to note is that, you know, in the example of the Potts model, polymers gamma came with a natural notion of size. Okay, so this is different than the multivariate hardcore model. And the size, let's say the size of gamma is just the number of vertices of the subgraph. And so I drew some polymers of size 1, and I also drew a couple of polymers of size 2. But this actually is what makes things interesting here. When we're talking about polymers that are subgraphs of some host graph, this notion of size will come in very useful. And a lot of times we'll take, you know, often we take A of gamma to be the size of gamma, and B of gamma maybe to be some constant times the size of gamma. Okay, and so then these functions A and B in the Kotetsky price condition really have a much more natural interpretation. They're not just some arbitrary functions, but they're proportional to this notion of size, and where size really comes from the fact that these polymers live in some host graph, and compatibility is defined in terms of the graph metric on this host graph. Good. So one thing, and I won't go over this now, one thing is that you can do all the stuff that we talked about, cumulants, joint cumulants, correlation, decay, all of that stuff translates directly. So if you have a convergent cluster expansion for your abstract polymer model, you can compute with a series, you can compute expectations, you can compute variance, you can show large deviation bounds, you can show correlation decay. All of that stuff you can do. And so once you get the convergence of the cluster expansion, anything you want to know probabilistically, you can find out. And so that's really our goal. Good. So let me show you the notes, pull up the notes, and show you what we'll do next. Okay, and so I want to emphasize these 3 steps. And so now we're looking at some model with strong interactions, maybe the Potts model when beta is large. And so what do we want to do to understand this low temperature model by switching perspective. The first thing is what we did already. We want to express small deviations. Okay, that's the part that we need to define. Small deviations from the ground state as this abstract polymer model. And we want to be sure that the weight factorizes over polymers. Okay, so we started that with the POTS model. We want to check the convergence of the cluster expansion, right? So we need to verify the Kotetsky price condition. And then this step 3, this is the part that we haven't talked about, but if there's more than one ground state, so in the POTS model, there's these q different ground states. And if you have a model, let's say a hardcore model on a bipartite graph, like we saw in the pictures, there might be 2 ground states, even dominated, odd dominated. What we would like to do is we would like to approximate the partition function of the full model as the sum of these different polymer model partition functions, scaled appropriately. So we would like to say that the POTS model partition function is approximately the red dominated plus the blue dominated plus the green dominated. Okay, but this really takes a proof. And what you want to do is, the picture we should have in mind is now I'm going to draw the state space. Okay, so now I'm going to draw the state space of the POTS model. So here are now vertices of this picture, or points in this picture, are configurations. What we sort of expect for the low temperature POTS model is we have, here's red dominated, here's blue dominated, here's green dominated configurations. And we expect, that in the state space, there are these exponentially small cuts separating these big pieces of the state space.
Sorry, so you connect two states by an edge if they differ in like one coordinate or something?
Exactly, yeah. From a computer science perspective, this is very natural. You think of like a Markov chain, Glauber dynamics, which samples a configuration by updating one spin at a time. And this is like the graph of where you can get to in one step with that. And of course, the picture I've drawn, it really depends on beta. If beta is very small, then we really just think of like one big blob of disordered states. But I want to think as beta changes, the weights of configurations change, and so the picture changes. And if we can prove a picture like this, and what do I mean? What do I mean? I mean that, like, if you ignore these like exponentially small bits that connect, then we can really say that the partition function is the sum of the red, the blue, the green. Okay, and then if we can approximate with this polymer model and the cluster expansion, the red dominated configurations and the green dominated and the blue, then we can sum them together. The cool thing is that proving such a result, this is a very, very well studied topic in computer science. This is proving a slow mixing result. Okay, so I haven't talked about Markov chains, but if you know Markov chains, showing that that these bits in the middle are exponentially small is proving that certain Markov chains mix slowly. And so that actually is a really useful step in approximating a partition function at low temperatures. Good. And then what do I say here? I say if we can carry out these steps, then we get a few things. The first is we get this counting result. Okay? This might be the most useful for combinatorics. We get a good approximation of the partition function as the sum of these partition functions. We also get, in a sense, a probabilistic approximation. The Gibbs measure of the full POTS model is well approximated by flipping a q-sided coin and then picking a random polymer configuration that measures deviations from whichever color came up on the coin. And then we don't, as we said, we don't have correlation decay. We have long-range correlations, but we have some sense of conditional correlation decay. If we condition on our configuration being, say, in the green-dominated set of configurations, then we actually recover exponential decay of correlations. even though it doesn't hold for the full model. Okay, so that's somehow the high-level view of the steps. And I'll start just with an example. And this example I'm choosing just because it's relatively simple. And so we're going to look at the Potts model on a max degree delta expander graph. And so here I'm going to talk about edge expansion. And so the condition that it will satisfy will be for some alpha greater than 0, the number of edges that go out of a set S is at least alpha times the size of the set S for all subsets S of size at most half the graph. Okay, so this is some edge expansion condition. A set of size of 100 vertices has at least alpha times 100 edges going out. Okay, and this will help us verify the Kotetsky price condition. Good, and so we define polymers. Let's focus on red. Focus on red-dominated configurations. And polymers now will be connected.
Oh, sorry, just a short question. So you don't want to normalize this by delta, so it's not alpha delta times S.
No, alpha might depend on delta. That's fine. That's fine. So in like the random delta regular graph, alpha it grows with delta. In fact, yeah. But for now, it's fine just to take alpha. And our parameters will be some function of beta, delta, alpha, and so on. So polymers will be connected induced subgraphs colored by the Q-1 non-red colors, just as before. But these connected induced subgraphs will be of size less than n/2. Okay, so that's the only change from the previous polymer model, that we insist that these defect polymers are bounded in size. So they can't be this big blue blob that dominate the thing. And we're hoping that this is enough to actually just capture deviations from the ground state. Okay. And again, what was the weight function? Weight of gamma was e to the minus beta times the outgoing edge boundary. Minus beta times the number of bichromatic edges in gamma. Okay, but already we can put an upper bound, right? So to check convergence, we want these weights to be small. We already know this is at most e to the minus beta times alpha, times size of S, or sorry, size of gamma by expansion. And we can ignore the other term in the exponent because that only helps us get it smaller. Okay, so we have a nice bound on the weight functions. We also need a bound on the number of gamma prime that are incompatible with gamma. And here we'll use like a simple lemma. This appears in a couple papers, including Galvin and Kahn. The number of connected induced subgraphs of G of size K containing V, containing some fixed vertex, is at most E delta to the K. So delta, again, here, it's the regularity or the max degree, but there's some exponential bound on the number of connected induced subgraphs that contain a given vertex. Okay, and so we can actually now already verify Kotetsky price condition if beta is large enough. So let A of gamma equal B of gamma equal the size. So again, the size is the number of vertices in this induced subgraph. And so we have we want to look at sum over gamma prime incompatible with gamma. Weights, I'll remove the absolute values since I'm thinking of the weights as being non-negative. Okay, so this is at most, and now I'm going to sum over all the possible sizes of gamma prime. So K is the size of these this polymer that's incompatible. What's the number of possible polymers of size K that are incompatible with gamma? So, well, we basically have something like delta times the size of gamma ways to neighbor gamma. And then we have a factor that's like E delta. E delta to the K would be the number of connected induced subgraphs. We also have to have a Q minus 1 for the number of ways to color this connected induced subgraph with the non-red colors. So this is a bound on the number of polymers of size K incompatible with gamma. And then we have this E to the 2K for the E to the A of gamma plus B of gamma. And then we have the weight function, which is at most E to the minus alpha beta K. Right? And that's from this bound here. Okay, so some things pop out. So we got a size of gamma, we got a delta, and then we got a sum K at least 1 of some exponential. K multiplies everything, and then what do we get? We get something like 3 plus log delta plus log Q. And then the important one is minus alpha beta. Okay, and basically we want whatever is in here to be negative enough that this exponential series converges and kills off the delta, right? Because we want this to be less than size of gamma, which is A of gamma. Okay, and so it suffices, and I'll let you do the algebra, but suffices to take beta at least 4 plus 2 log Q delta over alpha. Okay, and then what do we get? We get Kotetsky price condition holds, convergence of cluster expansion, and so on. And I sort of illustrate in the notes, but I also give a reference. But it's actually the slow mixing results showing that the sum of these polymer model partition functions is a good approximation of the full partition function. This also is actually quite easy, and it follows directly from expansion. Basically, if you have too many big pieces of different colors, there's going to be lots of bichromatic edges that you get penalized in your weight. And so really, what this shows is that if beta is this large, you have great control over these restricted partition functions dominated by the different colors. And this actually completely describes the whole model. Asymptotics of the partition function, the Gibbs measure is well approximated by some simpler measure, and so on. So I'll stop there today, and then what I'll do next time is do a real combinatorial example to really give you an idea how to apply this in combinatorics.
Great, thanks a lot, Will. So for this expansion part in the so it's at the end of this 4.41. You refer to some other paper. Okay. So it would be, for me, it would be interesting to see how this is. How this works.
How the approximation?
Yeah, like this relation between the slow mixing and the
yeah. I can say a couple words at the start of next time, but I mean, you could also go to this paper 24, and that's where we do this. I mean, it's really, the proof is like a couple paragraphs.
Okay.
But the point is that if you don't have one dominant color, then you have to have a lot of bichromatic edges, and these are penalized exponentially, especially when beta is large.
Yeah, okay.
It's actually much easier than the typical slow mixing proofs that you see in computer science, where they're working with ZD or something like this, where you really have to do contours and so on. The expansion somehow covers everything.
Okay.
I'll also say after the last lecture Tuesday, I'll have office hours again if you want to ask questions about the exercises, and I'll type up some sheet that gives you some hints to the exercises. I know some people started them, and we had a good discussion during the office hours about them.
So Will, since you have slow mixing for the hardcore model at low temperature, it suggests the question of how you generated the pictures of the low temperature hardcore model on the torus that you showed us earlier. I mean, maybe using coupling from the past or something.
No, I cheated, but I cheated in a way that I actually think is not cheating. And so what I did was I just started from like all even or all odd occupied.
Oh, I see.
Well, so here's a great open question for you. So actually, recently we proved that there are efficient algorithms to sample from, say, the torus, using this whole Pure-Gaussian, so on and so on. But really, the right algorithm should be flip a coin, even or odd, and start at the ground state and run Glauber. And the conjecture is that at low enough temperature, this in time n log n will get you a sample. Even though it doesn't mix, but you somehow avoided the slow mixing by flipping the coin to start. But we don't know how to prove that. That's actually, it seems really hard to prove.
It turns out that for pretty large toruses, larger than the ones that you pictured, you can use coupling from the past combined with a very fast Markov chain to get exactly random configurations.
From at low temperature or low?
At low temperature, yes. Yeah.
Oh, wow.
Amazingly low.
Okay.
It's because the process is so efficient that it just overcomes
right.
Slow mixing. That's what Peter Shore and I did years ago.
Oh, very nice.
With much lower computing power than we now have.
Yeah.
I'll tell you about it some other time. So.
Yeah. But I definitely got these by cheating, by starting where I wanted to start.
Yeah. So it does raise the philosophical question here. Suppose you had done it and ended up with a solid red picture. Would you have shown us that picture, or would you have tried it again?
I did end up with a solid red picture because I put lambda as like 8.1, and then I switched to lambda as 4.1, so we got a different picture.
Right. Okay. Well, yes.
So you're right. But I mean, it is an important point to bring up that once you switch perspective, everything becomes easier the larger lambda or beta is, which is like the opposite.
That's the very cool thing that comes out of this. It's marvelous.
Yeah.
Will, I also have one question about these polymers. So it's only about pairwise interactions again. So is there an analog for higher kind of incompatibilities and so on? Or is it the same story as with this hypergraph?
It's the same story.
Process?
So certainly people would be interested in multi-body or hypergraph interactions. It's just much harder to control these error terms in the cluster expansion. And so when they do analyze multi-body interactions, usually they find a way to massage the model and reduce to a pairwise interaction model. Because we have all these nice convergence criteria. But yeah, I mean, you can certainly define a model like that, and it makes sense and it's useful. The question is, how do you show convergence? And maybe it's best to somehow reduce to pairwise.
Okay.
So with this mechanism, it looks like you'd be able to analyze wolf shapes and all kinds of cool stuff like that. I mean, figure out what typical large defects look like, for example.
Exactly. Yeah. So you can I mean, and this is the idea of Pure-Gaussian theory in general, that you can really understand very precisely the probabilistic thing. So, I mean, in this case, in ZD, for example, low temperatures, the defects their boundary is size at most log n, and we can understand their law. I mean, what you bring up though is even maybe more interesting, which is what can we say at criticality when we have a real competition between different phases? That's much more subtle and interesting. But you know, one thing I'll bring up at the very end of the lectures is there's some very nice combinatorics questions motivated by that thought. What does it look like when you have an interface? And what does that look like in a combinatorics problem? What's an interface?
Right. Okay. Great.
Thank you, everyone. See you Tuesday for the last one.
Right.
Yeah.
Bye-bye.
Thanks, Will, and see you Tuesday. Bye bye.
Bye.
Thanks, Will.